reference, like size 15 reference string, and just do all the what's it called? All the replacement algorithm and mapping algorithms. I think that would be the best. Maybe. Not sure. So let me see. So I guess someone just give me a reference string, just type it in the chat, and then I guess we'll go over that. And we'll use size cache size 4. Nothing too big. Alright, sure, yeah. Let's use that. It's good, it has some repetition, it's got everything. Let me just copy it and then I'll share my screen in a bit. Alright, let me share my screen. Alright. So this is the reference string. I guess the first thing we'll do is direct. Direct mapping uses a trivial replacement algorithm. With direct mapping, the way you map things, is just the reference mod cache size. Let's say the first one, obviously it's a miss, it's not in the cache. And then where does it go? It goes in the 1, which is the reference. Mod cache size, we're using cache size 4. So 1 mod 4 goes in location 1. And then 3 is a miss. 3 mod 4 is location 3. And then 4 is also a miss because it's not in the cache. So it goes in location 4 mod 4 is 0, goes here. 9's a miss. Hold on. 9's a miss. It goes in 9 mod 4, which is location 1. And when we replace in direct mapping, it uses a trivial replacement, which just means just replace whatever it lands on, just replace it. Doesn't matter. So 9 mod 4 is gonna be 1. It's gonna go in location 1, but location 1 already has 1 in it. So it's just gonna replace it. And then 2 is a miss, and it goes in location 2. Because 2 mod 4 is 2. Then 6 6 is also a miss. It goes in 6 mod 4, which is 2. So it just kicks out 2, goes in location 2. 7's a miss. 7 mod 4 is 3. Kicks out 3 from location 3. 8's a miss. 8 mod 4 is 0. In location 0 we have 4. We kick out 4. Alright. 5's a miss. 5 mod 4 is 1. Goes in location 1. 4 is a miss. Just gonna go through this a little quick because it's the easiest one. 6 is a hit. Nothing happens to the cache. The hit, nothing changes from here to here. 2 is a miss. 2 mod 4 is 2. Places 6. 1 is a it's a miss. The miss goes here. 1's a hit because it's in the cache. 1 4 1 2 7. Cache doesn't change. 6 is a miss. 6 mod 4 is 2, so it goes here. Alright, our memory time is always hits times cache time plus misses times memory time plus penalty. So if you say like he's gonna give us like cache time, I don't know, 3, memory time 27, and then penalty is like 2, then this would be the number of hits is we had only 2 hits. Because 2 times the cache time, which is 3, plus 13 times 27 memory time plus 2 NS penalty time. Alright, that's direct. Now, the next one is just fully associative mapping with LRU, with FIFO replacement. The basic one. So basically means like whichever address came in first is the one you replace.
Sorry to interrupt, but he
Yeah.
mentioned it during the review yesterday that he's gonna put FIFO in the exam, right?
I don't know. I have no clue.
I'm pretty sure it's in the video that was posted.
Oh, he said that?
Yeah, he said that like he was like, oh, I'm gonna put the hardest one. What is the hardest one? He egged everyone to say FIFO, which is the easiest one, and he's like, okay,
I'll see. I don't think it's gonna be FIFO, but I think he was joking, honestly.
we'll see. Yeah.
Alright, but with fully associative mapping, the way you map things, mapping just goes from 0 to whatever, 0 to 4. So first come, first serve, basically. And then replacement is, alright, and let's just see what that means. 1's a miss, so it just goes in the first location. 1. Oops. 3 is a miss, it goes in the second location. 4 is a miss, it goes in the third location. That's what it means by first come, first serve. 9's a miss, 1, 3, 4, 9. 2 is a miss, but it has no space. So we replace whatever came in first. 1 came in first, so that gets replaced. 1 gets kicked. 3, 4, 9. And then 6 is a miss. Now, our first in now is 3, because that's what came after 1. But 1 was already placed. 3 is the next one that was first in. So 2, 3 gets replaced, 4 and 9 stay. Now our next in is 4, just to keep in mind. 7 is a miss, 2, 6, 4 gets replaced, and 9. Now our next in is 9. 8 is a miss, so 9 gets replaced, 2, 6, 7, 8. 5 is also a miss. Now the one that came in first, based on these 4, is 2. Because 6, 7, 8 all came after it, right here. So 2 gets replaced. 4 is a miss. 6 gets replaced because it came in first. 6 is a miss because we just removed it. 7 gets replaced. 2 is a miss. 8 gets replaced. Right, because 5, 4, 6, 8. 6, 4, 5, 8 came in first. Now he's least recently used. It's whichever one came in first. In this example, it kind of looks like least recently used, but it's not. But I know the difference. 1 is a miss. 5, 4, 6. Wait. Yeah. But in this case, between 5, 4, 6, and 2, 5 was the one that came in first, so it gets replaced. 1's a hit. 1, 4, 6, 2. And 6 is a hit. And then that's it. We have 2 hits, 13 misses again. Alright. Now it's fully associative. Next one is LRU replacement. Just means the address that was least recently used. Honestly, this string is not very good, but well, I guess we'll deal with it. Actually, maybe I'll change it up a little. Like, all right. The mapping is again first come, first serve, because of fully associative mapping. The only time it's not first come, first serve is when he says direct mapping. Otherwise, it's just first come. And then the replacement, LRU, least recently used. And yeah, we'll see what that means now. Hold on. Alright. 1's a miss. Again, it just goes straight into the cache. First come, first serve. 3's a miss. 4's a miss. 3's a hit. Nothing happens. 2 is a miss. Now 6 is a miss, but there's no space, so one of them needs. Now we gotta use a replacement algorithm. Now we check. We have 1, 3, 4, 2 in the cache. Which one is least recently used? So let's go back till we find all of them. 2, 3, 4, and 1. With LRU, we always trace back. Trace back until we found all 4 of these numbers. 2, 3, 4, 1. And then you take the leftmost one, gets removed. In that case, 1, because it was least recently used. 1 is here, so location 0 gets replaced. 4 is a hit. 6 is a hit. 5 is a miss. Okay, now we look again. look back. 6, 3, 4, 2. Which one was least recently used? We found 6, we found 4, and we still need 3 and 2. 2, 3. Okay, we found all 4. Now 3 is the leftmost one. That means it was least recently used. So 3 gets replaced. 3 is right here. 5 replaces 3. 6, 4. 4 is a hit. 6 is a hit. I guess this string wasn't very good. 6, 5, 2. Okay, one's a miss. Alright. Again, trace back till we found 6, 5, 4, and 2. Found 2, found 6, found 4, and found 5. That's it, I stop. Whichever one is the leftmost is the one that gets replaced. 5 is the leftmost, so 5 gets replaced. One's a hit. And 6 a hit.
I have actually a doubt.
Yes.
So why we stopped at like 5? You said like when we miss one, you said go back and try to search the elements in the least recently used, and you stop at like fifth address.
Yeah, if there's like a collision, so like here there was a collision. To find which one to replace, we look at our cache. Well, what's in our cache? 6, 5, 4, and 2. And then we look back till we found all 4. So we need 2, 4, 5, 6. I found 2, found 6, found 4, I found 5. Once you found all 4 of them,
Oh,
or
okay.
however many, then you take the leftmost one as the one to replace. Because it came in, it was the least recently used. These are more recently used, basically.
Okay.
I feel like this TMA crap is okay. 1, 2, 3, 4, 5. 8 hits, 7 misses. We'll never calculate this. The next one is optimal. Yeah. Again, fully associative, first come, first serve. That's what he means by OPT is optimal. It's not a real algorithm. It's like for benchmarking. Like, oh, what is the best? You know, it's not. It's ideal, but it's not realistic. Okay. It's kind of the same as LRU, but instead of looking to the left, you look to the right. Basically, look to the future. One's a miss. Three is miss. 4 is a miss. 9 is a miss. 2 is a miss, but it's a collision miss. So now we basically we look forward 1, 3, 4, and 9 till we found them. Found 4, 1, and that's it. So 3 and 9 are never going to be used again. But we can replace whichever one. In this case, we'll replace 3 because it was first in. 6 is a miss. Do the same thing. Look to the right. 1, 2, 4, and 9. Found 4, I found 1. Again, 2 and 9 are never going to be used. So let's replace 2. 7's a miss. Again. 1, 6, 4, 9, we gotta find them. I only found 6 and 1. They're gonna be used in the future, but 4 and 9 are not gonna be used. So let's replace 4. Again, 8 is a miss. 1679. 5, 4. I found 6, I found 1. 7 and 9 are never going to be used again. So let's replace 7. Five is a miss. Again. 1 and 6, no 8 and 9. So let's replace 8. Four is a miss. Again, 1 and 6, no 5, no 9. Let's replace 5. Six is a hit. Two is a miss. We gotta find 1, 6, 4, and 9. Found 1, found 6, no 4, no 9. So 4 gets replaced. 1s are hits. And 6 is a hit. Okay. And then this is, hits. Four hits. 1, yeah. 4 hits, 11 misses.
I have another question.
Yeah.
So if you see on the second address, like you got a miss for the second address, and before the second address, you have the elements 1649. Yep, this one 1649, and because you got the miss on the second address, so you updated the element on the fourth. You updated the element on the fourth because you said like we don't have in the future, but we also don't have the 9 in the future. So why we didn't upload the 9?
It doesn't really matter which one you replace, but I guess we could use like whichever was first in.
Okay, and also like for example, if we got a like string in which is we have
You
like
mean like yeah. You know what? Yeah, 9 should have been replaced at some point. It doesn't really matter though which one you replace. In this case, we
so
just replaced the one that came earlier in the cache. I don't know.
okay, and for example, if we got a case in which we have two least addresses in the future, like two equal least addresses in the future. So which one are you gonna like? Which one you gonna change or something?
Yeah, we had that. Like, oh, you mean like, yeah, if there's like, yeah, I get what you mean.
People are saying in the chat to use first.
No, but the thing is, there's no such like, look, if we had like, I don't know, let's see. Okay, let's say we're over here. Sorry. And then we want to put 7 in. 1649. Say this is 9. And this is a 4. So then we look to the right till we found all 4 of these. Right? We found 4, 6, 1, and 9. All are 4 over here. So we found them. So then the rightmost one is the one to replace. Unlike in LRU, the leftmost one was the one to replace. Here's the rightmost one. So 9 would be replaced. It doesn't matter if you have, like, I don't know, if you have a 9 over here. I mean, if you had like another 6 here, or like a 4 here, whichever one is the rightmost is the one to replace in any case.
I got you.
Like it would be 1, 6, 4, 7. That's what the block algorithm. Did I miss one? I feel like I missed one. Oh yeah, LFU. Okay, it's just first come first serve. And then here's a miss, collision miss. Now least frequently used. And by the way, if there is a tie, so the first in gets replaced. In this case, 1 is used once, 3 is used once, 4 is used once, 9 is used once. So they're all used once. So we'll replace the one that came in first. We just use first in replacement. Six is also a miss. Let's see, 2, 3, 4, and 9. 2 is used once, 9 is used once, 4 is used once, 3 is used once. Again, we replace the first in. First in now is 3. It's the one that was the next first, basically. Seven is a miss. And why did it replace 4? Because 2, 6, 4, and 9 were only used once each. Alright. 8 is a miss. 2, 6, 7, 9 were all used once each. Places 9, why? Because 9 was the next first in. Replace these 3, 9 is next. Alright. Until we don't have a hit, then this is basically just like the first one we did. This one. Before replacement. Until there's a hit. Then something might be different. This reference string is pretty bad for all of these. Again, 2 was our next first in. We replaced 9, now it's 2. 5, 6, 7, 8. We're just replacing the first ins because actually wait. 5, 6, 7. Yeah, all reference once. 6 is another miss. Four is a hit. So now keep in mind 4 was used twice. Let's put an I next to it, meaning it's got some weight. It was used twice, so if none of these have a 1 next to them, they're gonna be considered first. This is not gonna be considered until something matches it. 1 is a miss. So now 5, 6, and 8. 6, 5, 8. Wait. 6 was used twice. So, hold on, wait. This one easier to do with the table then. No, never mind. Yeah, we don't consider this because 6 was never a hit. It just got replaced, so it doesn't count as it being used twice. 6 was only used once. Now the one that gets replaced, let's see. Our next first in, which is 8. One is a hit. Now one also carries that value because it's been referenced twice already. And 9 is a miss. Between 5 and 6, 5 came in first. So 5 gets replaced. He made 2 hits, 13 misses.
When we getting the hits, you updating 4,1.
Hmm?
Yeah, was this like 4,1 in the hits?
Well, it means like it's been referenced twice since there was a hit.
Okay.
So now like if there was another hit with a 4, then 4 would have 4,2. Like it's just a tally. Tally how many times it had a hit. And then there's set associative with all of them, all of the replacement. But set associative is like the same as fully associative, but it's just like you divide into sets. And the way you know which set it's going to is like the memory reference mod number of sets. So I think let me just go over one. Yeah, like this. So like this is two-way. Two-way meaning like in each set we're gonna have 2 elements, two blocks. And since this cache is size 4, we're only gonna have 2 sets. 4 divided by 2. And with LRU, like set associative is like fully associative but with sets. It's less computational, I guess. So when you have like when you're keeping track of a bit with two-way set associative, you're gonna be keeping track of a bit in the first set and in the second set. So for example, here 1 is a miss. 1, to determine which set it goes to, you do 1 mod the number of sets. We have 2 sets. So it goes in set 1. This is set 0, this is set 1. And with set associative, you always use first come, first serve. So it goes in the first spot of the second set. And a 2 is a miss. It goes in the first set. It's 2 mod 2 is 0. And then underline meaning they're the least recently used in their own set. And then 1 was a hit, nothing happens. 3 is a miss. It goes after 1 in the second set. Because 3 mod 2 is 1. So set 1. And then 2 is a hit. 4 goes after 2. And then 1's a hit, 4 is a hit. 5 is a miss. So then 5 places the least recently used. So you check between 1 and 3. Which one is least recently used? Go back, I found 1. 3 is less recently used than 1. So 3 gets replaced with 5.
Wait, can you go back and explain why for the first one it's at 2? It's 1 mod 2, which is 1, but why is it at 2?
Oh yeah, it's when we do the mod for set associative, it determines which set it's going to. So this is set 0, this is set 1. It's not, don't look at these indexes, set associative.
Okay.
You only look at the indices for direct.
Okay, so
Set
whatever you
associative, so
get from 1 mod 2, it'll always be set 0 or set 1. Like it'll be like 1 or 0.
yeah.
If I'm guessing, like there is no mod that would give you like a 2 or something, right? Because it's only a two-way associate.
Yeah, in this case, no.
Okay.
Then the
there
way you
ever
place them, you just put them first come, first serve. Just fill it up from top bottom.
Okay, thank you.
Anyway, these are all hits, and then 3's a miss. It goes in the odd set. And we have 1 and 5 in the cache. We found 1 and 5. 5 comes before 1. Least recently used, so it gets replaced with a 3. That's basically two-way. That's basically set associative. You could have 3 sets, 4 sets, it's all the same thing. And then there's a clock algorithm. Yeah. I think this is a good example. So we're given this reference string, and we're mapping it with fully associative mapping, size 4, and we use second chance clock replacement. So in this example, I use like an arrow pointing to a block, indicating that the block is the next one to be evaluated for replacement. From the beginning, when you're only inserting elements using first come, first serve, the clock hand is in block 0. You insert the first one, which is 2. And the bit is 0, second chance bit. Second chance bit is if it had a hit. If it had a hit, then it turns to 1. And then you'll see what that does later. So, anyway, as we insert, the clock hand moves with whatever we're inserting. So when we have space, we're just moving the hand down and inserting the elements. And then when we're full, the clock hand moves up to the first element, and it stays there. Now for our fifth one, 1, 2, 3, 4, 5 is a 2. 2 is a hit. So now since 2 is a hit, its bit turns to 1. That's just how it works. That means like second chance. It's given a second chance. Now our sixth element is a 3. We're looking in the cache. 3 is a hit. Yes, it's in the cache. So 3's second chance bit turns to a 1. Clock hand doesn't move. If there's hits, nothing happens to the clock hand. Alright, then our next one is 6. Okay. 6 is a hit. Its second chance bit turns to a 1. Nothing happens to the clock. Alright. Then we have a 5. 5 is a miss. So we look here. So this clock hand looks at whatever it's pointing, and it's like, okay, 2, do you have a second chance bit? Yes, it does. So the second chance bit turns to a 0, turns it to a 0, and then the clock hand moves to the next location. Oops. Wherever that one. Checks 1. 1 has a bit, so that bit turns to a 0, and then it keeps going until it finds a 0. This one doesn't have a second chance bit, it's a 0. So then this one gets replaced. 5 replaces 4. And then our clock hand ends up in the next location, which is 3. Right here. And the clock hand doesn't move unless there's another miss. So for example, after that we have 2. 2 is a hit, so nothing happens. 2's bit turns to a 1 since it was a hit. The only thing that happens in a hit is that the value that got the hit, the bit changes to a 1. And if it was already a 1, it stays a 1. It doesn't turn into a 2 or 1, 1, whatever. And then we have a 6. 6 is a hit. But if you can see, 6 already had a second chance bit. So 6's second chance bit stays the same. Still got the second chance. There's no third chance. And then again we have a 6. Stays the same because it already had a second chance bit. And the last thing is a 7. So the hand is here, it's going to evaluate this. 6 has a second chance, turns it to a 0, then it moves up. 0 has a second chance, turns it to a 0, then it checks, it goes down again. 1 doesn't have a second chance, so the element at block 1 gets replaced. 3 gets replaced with 7, and the clock moves down. And that's it. That's pretty much it. I don't know how you do this with a table, but I think if you have scrap, you can just quickly sketch out like little tables like this with the clock hand so that you keep yourself organized. And the same for LFU, because LFU, you would have like next to like here LFU, you'd have a tally of the number of times it was used. So for example, like that. And that's not very easy to do using his table. If that makes sense. I think that's it, right?
Could you go over like where you go for like the values or like PC during the code stage and stuff? I'm not really understanding that part.
Oh, you mean like the first few questions of the exam?
Yeah, like the MAR values at like which stage in each stage, like that. That got me hella confused.
Yeah, it's basically all right here. I think I sent this.
Oh, you did?
But yeah, whenever you see change, it changes. And actually, let me like.
Wait, did you send this like document, or you just like showed it briefly?
Oh yeah, I sent it.
Oh snap! All right, I'm slacking. I don't even see it.
Yo,
Uh,
can you send the algorithms document in the Discord?
Yeah, sure. I'll send it later, like maybe in the morning tomorrow, cause I gotta print something and then
Yeah,
I'll,
thank you.
I gotta organize. Otherwise, I'm gonna be a mess.
honestly, I don't even see the document.
You mean like? No, I sent this, like a picture of this.
Oh, a picture.
Yeah.
All right, I'll try to look for it. Thanks.
Mm-hmm. Basically, whenever it changes here is the last time it changes. So like if it says, "Oh, what's the value of PC after the decode stage for this instruction?" for example, then the last time PC changed was here. PC basically points to this program's and this instruction's address plus 4. Plus 4 means like the next instruction's address. So if this was the next instruction, it would point to this instruction's address. Let's say this address was like 24, this was 28. The value of PC in the decode stage would already be 28 because it was already updated at the end of the fetch stage.
Right. So, like, let's say for like the store one, if they ask for like the MAR value like before exact, would that just be? I don't know what that would be actually.
So yeah, so this is a store. So before exec, in exec it changes. For
All right.
exec, the last time it changes is right here. So that means it would be the address of this instruction.
Oh, okay.
So if this was 28,
Then MAR would be 28, right?
the MAR, yeah, would be address 28. So like this.
Okay. So then after it would be whatever was in R3, the value of R3.
No, after the exec, it's gonna be wherever you're going in memory. So whatever's in the brackets,
Oh, okay, okay.
store. Because MAR only has the address. MDR has the data, and the control has either read or write, or other
Right,
control.
right. Okay, thank you.
Mm-hmm. But yeah, I guess that's it. I'm gonna stop sharing now. All right. Good night. Thank you, everyone.
Night.
Good night.